Test. 2 seconds. Good morning. Okay. Today maybe is the last lecture. Next, maybe Wednesday. Yeah, I think just revision. I hope today can finish this topic by part-type graph about the matching problem and using the maximum floor algorithm or Focusson method to solve the matching problem. Of course, you can solve a lot of problems. Yeah, one I trying to focus on matching problem only here. I think I'm not discussing the proof. The proof is a bit tedious. Maybe should be 2000. I think it's 2000 module should discuss about the proof. I'm trying to discuss more on the implementation or what this algorithm is about first. So at least you understand the algorithm, you know what it is, you know how to implement it. Well, maybe you can't implement it in a very efficient way, or you don't understand the time complexity, is fine. Because next level, when they're talking about more detail about the graph, more detail in all the algorithm analysis, they should be able to, you should be able to prove this time complexity of graph problem. The time complexity, actually not easy. Sometimes you need to, there's some logic thinking. You need to use some logic thinking to understand the idea behind the proof. Okay. Maybe wait for another 5 minutes. Okay, another thing, I think this week there's no tutorial. The last tutorial will be in week 13. I think I was release the solution in maybe Friday. Next Friday also together, everything. Then this week there's a lab. There's a lab 7 and lab 8 next week. So this week will be only one lab. Unless your tutor have other arrangement for this week. Otherwise, the last topic should be covered in next. The tutorial will be covered in next week, week 13, the last week. So at least trying to give you an opportunity to clarify your doubt. During the last tutorial section in week 13. And lab-wise, lab 7 and lab 8 will be conducted in this week and next week respectively. And then assignment, the last 2 assignment is combined into one. So that's been 10%. Okay, that's been 10%. And the deadline will be also in week 13, Saturday, 11:59. I really try my best. Usually you will find some people maybe find that sometimes they still can have extra a few more minutes to finish out their lab, the assignment. Yes, I didn't go and maybe the system allowed, the server they didn't update the timing on time, but I try not to manually end the test. Normally I end the test in the second day, maybe in the lunchtime around that. After I having lunch, I just go and end the test. So that is the best I can do. Yeah, I already trying to give as many time, as much as I can. But we cannot delay too much because especially the last one is already week 13. Yeah. So have to take notes. The deadline. Anything I need to set? The tutorial. Okay, the lab test will be 2 hours. That's mean 3 coding question and programming and the MCQ. So there's a final quiz and the lab test together in 2 hours. The venue and the schedule will be released in these 2 days. Yeah, so please take notes the announcement. Yeah, I'm arranging. So, but quite clear. I think one thing is it's 2 hours. It's quiz and the lab test too together. Yeah, it's very similar. The format is very similar to the assignment. Yeah, that's when there's some MCQ, then followed by the programming question. But the difficulty level, I would say MCQ, should be about the same. But the programming question, of course, should be easier lah. It cannot be too difficult. Yeah, because you only have, if I assume you can finish the MCQ in half an hour, that means you only have 1.5 hours to do the programming question. Actually, average, the difficulty level is something you can finish in half an hour. But the assignment, all this practice, the lab is for you to practice and familiar the C language and data structure and how to write the program, how to solve the problem. I think that is the learning outcome of this module. Okay, so, this is bipartite graph is the last topic I will cover in this module. Yeah, so we it is a we discuss only the matching problem, but the algorithm here is the maximum floor algorithm can solve a lot of problem. Later I will show you in the end. Will show you the possible application. Okay, so first, what is the matching problem? I think this thing I have shown you in the very first lecture. Yeah, one of the algorithm problem is matching problem. So first, let's say we have a graph that vertex V can be partitioned into 2 subsets. J, let's say I name it J and W. Maybe, that's in this set is J, and then this set is W, 2 subsets. Then these 2 subsets are disjoint set. That means every edge connect a vertex in J to 1 in W. So every edge is connect from here to here. Disjoint set, that means Tom and Harry are not connected. Tom and Dick are not connected. Cutting and polishing are not connected. Cutting and packaging are not connected. But Tom may connect to cutting. Tom may be connect to, there's an edge connect Tom and packaging. So this graph is known as bipartite graph. And then, what is the problem? Okay. So the problem is we need to find the matching. That means a subset of edge among these edges. You can see here, all the edges are mutually non-adjacency. And no 2 edges have an endpoint in common. So, where is my animation? Okay. So Oh, maybe too fast. Yeah. So this is the whole set of edges available. So my matching is trying to find these edges 1, 2, 3. Yeah. Such that a subset of edge that are mutually no agency. So there's no agency. This one is from Tom to packaging. So there's no agency connect Harry. There's no agency connect this edge. There's no path from packaging to cutting. There's no path Tom to cutting. Yeah. So they are non-agency. And then no two edge have an endpoint in common. Yeah. Tom only one. Yeah, there's no two edges. You can find no two edges having the endpoint in common. Yeah, that is matching. So my objective, my target is trying to find the maximum number of edges. So it's maximum matching. I wish to get as many match pair as possible. So how to solve this problem? Yeah, so maybe I need to introduce a source at one end. Another one is sink at the other end. And then trying to think that this is a directed graph. All of them are directed. Yeah, I'm trying to find a match from J to W. Yeah. All this become a directed graph. And I'm trying to think that maximum matching is trying to find the maximum flow. So this become a flow network, trying to find the flow from the source, maximum flow from the source to the sink. Yeah. And a flow is the directed graph in which each edge has non-negative capacity. For matching problem, that means all this is either 1 or 0. If there's a connection, there's a directed edge, then it's 1. If there's no directed edge, like 1 to from J1 to W6, yeah, the capacity is 1. You have 1 capacity. You can connect J1 to W6. But from J1 to W7, the capacity is 0 because there's no connection. There's no edge. Yeah. So now the problem from finding the maximum match, I need to find the maximum flow to maximize this. That means all these have the weight of 1. I didn't write because simply all of them are 1. Yeah, this is 1, this is 1, this is 1. The rest, there's no connection. That means they are 0. Their capacity is 0. Anyone I miss out? Okay, all are 1. Yeah, so I need to find the maximum flow. So not surprising at 1, 2, 3, 4, 5. You only have 5 edge flow out from the source, and only 4 edges, flow into the sink T. So maximum at most you can have 4, maybe, maybe 4, maybe maximum. For quite sure is from here you can see only 4. Here got 5. Yeah, you find one path from S to T. You only can find maximum up to 4. Maybe less than 4. Maybe less than 4. But maximum definitely is 4. Cannot be born at that. Because from here, W6, W7, W8, W9, there's only one edge connect to T. So you only can find 4. And each of them only have 1 capacity. That means you are not able to find 2 paths. That means if you find this way, for example, that means you cannot have, and this one cannot be selected. Yeah, this one cannot. This one cannot be selected. Okay, so the problem is trying to find the maximum flow, flowing from source S to the sink T. Yeah, so if that each of the edge only have 1 capacity, implied that W6 only can be selected once. Yeah, W7, W8, W9, J1, J2, J3, J4, J5. You only can select them once. Yeah, because the capacity only one. So once you formulate this problem in a maximum flow network, the flow network, as a flow network, the next thing is trying to use this Fogg-Fulkerson method. It is using an iterative improvement strategy proposed by two persons, Fogg and Fulkerson, in 1956. 1954, 1956. Around that time, they published a paper, then show this approach. So the basic idea is they iteratively finding an additional flow in the network and keep adding it until they cannot find any new flow in the network. That's mean that they achieve the maximum flow. Then they stop. Yeah. So to find the additional flow, they need, I think the key is this thing. They need this residue network. Basically, the idea is the complement of this network. I'm trying to use another residue network to record the available flow. Yeah, after I select one flow, yeah, what is the remaining available flow I can add in? Yeah, they need to use another residue network to find. So that's in today, if you have a matching problem, you have one graph. That's when you need to use this graph to create another graph called residue network for you to keep track the available flow. So that means this one, the residue network, the capacity, CF, I name it CF. So is the current network minus whatever flow you add in. So you expect that this CF will decrease over the times, because every time you find a new flow, if it's passing this particular edge JW, the capacity, the residue capacity will reduce. Yeah. But also can be the other way. You find that you need to flow in the other direction. Yeah, to cancel out. For the matching, that's when this match may be not appropriate. Later you will see, when you have one match not appropriate, you will find that in the residue network, there's an opposite direction for you to remove the early match and reselect another new match. Yeah, so that is the idea behind. So initially, so there's no any flow at the beginning. So just like this. Just now in the earlier slide, that is original network. This is the residue network. Yeah, but anyway, they are exactly the same. Oh, by the way, this slide is already put in the NTU Learn. If you need it, you can go and download it. So at the beginning, there's no flow. So the residue network is same as original given network at the beginning. So that's when I have a matching problem. I trying to reformulate this matching problem become a network flow problem. So I want to find the maximum flow. Then now I know that I need to iteratively find more and more additional flow in the network. I need a residue network. So I have the original network and residue network. Okay, so that is the key. The algorithm, the Fogg-Fulkerson method, is every iteration I'm trying to find a path. Yeah, an augmenting path from S to T, in the residue network, GF. I name it GF lah. So that means here I'm trying to find a path. The first path I found is this, from S to J1, W6 to T. The network, yes, based on the problem. So you need to, of course, the question they give you, they have to provide you all the match, all the possible pair, like J1, like just now the question, maybe here in the given question, J1 is trying to match with W6. J2 can match with W6 and W7. J3 can match with W7 and W8 and W9. Then J4, unfortunately, no corresponding pair in W. And then J5 is J6, W6 and W9. These are given. Of course, I have to give you. If I not give you, you have nothing to do. Yeah, there's no magic. The question have to provide you the problem, the data. Yeah, I cannot through any algorithm to guess what is the data. So this is given. The match is given. Just you don't know which one should eventually is the best match to maximize the match. Yeah. So you need to use this Ford-Fulkerson method. So Ford-Fulkerson method is trying to find the augmenting path. Yeah, as many as possible. So in the residue network, I have to emphasize in the residue network, not in the original network. Yeah, because the residue network playing the role is trying to tell you the balance of the capacity. How many capacity are available. Yeah, or in the matching problem, relatively simple because it's either 1 or 0. That means they only tell you in the residue network of the matching problem, they tell you is trying to tell you that the available path, the available match you can select in the network. So, just for example, yeah, at the beginning, let's say I select S, J1, W6, and T. So this is one of the possible match. That means select J1, trying to match with W6. Yeah. So and then after that, I will update my path. Yeah. That means I will just in the matching problem, because it's 1 and 0. That means now you no longer able to find. There's no capacity for you to find. There's no capacity from J1 to W6. But there's a capacity from the other direction now. From W6 to J1. What does it mean? That means later if I don't, due to some reason, for example, if I want to select J2 to match with W6, likely, if this is unlikely, later you'll find that this case cannot be. But if this is the case, that means you need to cancel this one. Yeah, you have to cancel this one. So you have to cancel this in the original network. So you find that in the residue network, they already give you they already have the message that, when you reverse this direction, later if you want to select W6 to match with any one of them, J2, J3, J4, or J5, I don't know. Yeah, but if you select this, one of them, maybe J5, implied that you definitely will select this one because your path, because you want to reach T, you definitely cannot go through W6. No more path directly from W6 to T. Yeah, you only can select from W6 to J1, then J1 back to S, maybe, or somewhere else. Then you can find a path to T. Right. So that is the good thing. That is the residue network trying to do. They're trying to give you store the information about the available flow, available capacity. So for you to find the path. And this path is trying to, in the matching problem, is trying to decide which pair in J to W in pair. How to select is J1 W6 or J2 W6 or J5 W6. Yeah. So let's say I select this one. Later you will see the example. Let's say, okay, first, this is the given problem. It's given. Okay, how J1 match with W6, J2 match with W6. Yeah, this is same as the earlier example. So the corresponding residue network, is exactly same as the original network at the beginning. I've seen all this. And then I didn't indicate because all of them, the capacity are equal to 1. And so on and so forth. So what does the flow in the previous slide? Okay, this is when I select a path, Okay, for the matching problem, you only can be 1. So that means the floor is 1. The floor is 1. If you select, that means it's -1. Then capacity for the matching problem is also 1. Either 1 or 0. So again, it's also only can be 1. Later you will see that when in the end, when I talk about when each edge there's a weight, there's a capacity, then yeah, it may not be 1. Yeah, I think earlier I have said that actually the floor or the capacity C is some non-negative. Non-negative, that means it can be 0, it can be some positive number, the capacity. Okay, so in the matching problem, it's either 1 or 0. Either you select it or not select it. Okay, so let's start. So now I already initialize, I create another graph. So what is this? So initially all the floor will be 0. There's no initially all the, what does it mean? That means, yeah, your residue network capacity will be same as the original network, given network, because this is 0. This one is 0 at the beginning, initially. Yeah, so you have two network, which is identical. Original network and residue network, starting they are the same. So in other words, whether there's an edge or there's no edge in the original graph, yeah, their flow initially all are 0. Yeah, flowing from U to V or V to U, all the flow are 0. Then your next is trying to find the path. And you this while loop, this part is keep trying to find the path. Every time you find one path, yeah, how to find a path? I think in the last week, yeah, we already teach you 2 methods to find a path. Do you know which one? Which algorithm you can find a path in the graph? If you give you a network, yes, breadth search and depth search. You are right. Yeah. So here I'm not discussing about the complexity, but breadth search and depth search, yeah, you can use it. These 2 methods can give you a path. Yeah. Which one better? Later, there's another issue. But both can give you one of them. You just need one of them. You don't need to both of them. You just need one of them. Okay. So either you use breadth search or depth search. They provide you a path from S to T in the residue network. Because only the residue network tell you where is any available flow, yeah, for you to select the augmenting path. So, and not surprising, starting the CF is non-zero. Cannot be 0. Yeah. Because they are equal. So, first, let's say I run using breadth search or depth search. They give me a path from S to J1 to W6 to T. Yes, I found it. Then my job is this part will be update the flow. So I will adding the flow to the corresponding edge. Yeah. So this one, of course, okay, should be this one first. First is what is the minimum, then 1 in this case. So it's 1. So yeah, you select the path. Back to just now. Yeah, this path. Yeah, this is 1. This is 1. This is 1. So among these 3 edges, the minimum is 1. Yeah. Later you will find that if the edge have some different capacity, yeah, your C minimum may not be 1, maybe some other number. It's among these 3 number. Among these 3, which one is the minimum. Yeah, the first one, S to J1, the edge from S to J1 is 1. J1 to W6 is 1. W6 to T, still 1. So 3, 1, 1, 1. No, the minimum is 1. Therefore, this minimum, in this case, for matching problem, this one is very simple. Actually, definitely always equal to 1. Then, so I'm trying to find at each edge in the path, along the path, I'm trying to update the flow. So just now the initially all these are 0. So now just increase by 1. So those corresponding edge, the flow of the corresponding edge in the corresponding edge will be equal to 1 now. This means I choose here, where is it now? Yeah, in red color. That means this one is 1, this one is 1, this one is 1. Yeah. So it's always 1 for matching problem only. Yeah. So, and then I will update my capacity. I will update my capacity in the residue graph. Update the residue graph. In the residue graph, which means originally my CF is same as the, again is for that particular edge is 1. Now minus 1, so it's 0. But at the same time, I will, in the reverse direction, originally is 0. There's no capacity in the opposite direction at the beginning. Then now I will increase by 1. In short, what this step trying to do, I will reverse my edge. I will reverse my direction. So you can see that I reverse the direction. Yeah, direction. In the residue graph. In other words, that means this path is already selected. J1 is matched with W6. Yeah, so that's the first step. Then next, again, you repeat one more times. Then now in the graph, you're trying to find another path from S to T. So this one definitely cannot already. So I have to select this. I think I select this one, and then followed by this one. Yes. Then after that, I select this one, repeat the same procedure. So in the network graph, I will select this one. Yeah, the flow will be increased to 1. In other words, there's no more capacity for me to flow from S to J2 after that because I already selected. I cannot select J2 second times. Each one only have one capacity. So you only can select J1, J2, J3, J4, J5 once. Same thing, W6, W7, W8, W9, you only can select them lightly once. Yeah, later you'll see why I said so. Okay, so again, same thing. I update my network graph, the flow. I also update my residue graph capacity. So you'll find that the edge will be switched the direction. All these edges, direction switch to the other way. Okay, one more time. Yeah, next one. Yeah, this one. J3W9 to T. Let's say this is the algorithm. They give me the path. Of course, you can see that this is not the only path. There's another one, J3 to W8 also can be. For the network graph to be updated. That's when I update the flow. In the algorithm, you can see that if it's inside the algorithm, they're trying to update the flow. Yeah. When the flow increase, implied that your residue capacity is decreased. Yeah. that means this particular edge is selected. For matching problem, it's quite simple because it's either 1 or 0. So so-called increase or decrease is just like 1 becomes 0, 0 become 1. So in that case, that means that particular edge is selected. Yeah, later you will see when I introduce the capacity to non-zero and 1, more than that. Yeah, that means the capacity can be any non-negative number. At that times, you will find that the flow increase, that means the usage of that particular path, particular edge increase. Yeah, more flow flowing through that particular edge. What does the code after the else mean? After the else. So the thing is, okay, that is one thing is I need to check whether in the graph, this particular edge is exists or not. So in starting just now, all the cases are this portion only, because all the edge is exists. Later I will show you the example when the second case happen. Okay, let's say same thing. This one I also select the third path. I also update. This one selected. Then this one was selected. Okay. Yeah, your question will be the next slide. So the next problem, the next thing, the next path is the key. The next path, you will find that if you're flowing here to here, this is the last one already. You select this one also cannot. You're flowing here to here, you have a problem. Yeah, you're flowing here to here to here to here, you start circulate. You only can select from here. Whatever that first search, breadth first search should be guide you that you have to flow to here. And then you have to flow to here. You have to flow to here. Okay, you reach T. Right? Yeah. So this path will be selected. Yeah, the algorithm breadth first search or depth first search, you apply. They return this path. Then you will find that this thing here, this one. When you're trying to update your original network at the left hand side, this edge doesn't exist. There's no edge from W9 to J3. You only have the edge from J3 to W9. Okay, what does it mean? It means that when I update my original network graph, this edge is not available. UV, that means from W9 to J3. There's no edge from W9 to J3. Not available. Then it's not the edge in the original graph. Thus, I need to minus 1. From V to VU, need to minus 1. What is VU? The opposite direction. I need to minus 1. That means I need to remove that particular augmenting edge, which I select earlier. I need to remove this red color one. The opposite direction. I need to cancel it out. So originally the definitely is 1. Then it will be minus 1. Will become 0. That means you're trying to remove it. So it's trying to remove a flow in the opposite direction. So it's removed. Then you will got this result. Just now is maybe change another color. Blue color. Just now the last augmenting path is in blue color. Is this one? I select this one. Okay, I better draw in the other one. Just now the augmenting graph is this one to this one to this one to this one and then to this one. Yeah. So after I update my graph, yeah, that is the result. you can see that actually this last omitting path trying to pair J5 with W9. At the same time, they remove the pair J3 and W9 and add a new pair, J3 pair with W8. So that to maximize, it's trying to maximize the number of matching. Yeah. So after this, you will find that no more. Yeah. You from S, you only can go to J4, but J4, yeah, there's no way to go further. That means you use breadth first search, depth first search, or any graph traversal algorithm. Not surprising, the answer is no more path. So you can stop. Yeah, then that is the answer. So that is the how to match J1 match with W6, J2 match with W7, J3 match with W8, J5 match with W9. One thing, take notes. This is not the problem. Recall the problem. My objective is trying to find the maximum match. There's a maximum number of match, just the maximum number. So which one pair with which one is not the problem we concern. Yeah, of course you can find a few solutions. Can I find a few solutions? 1, 2. Yeah, here this one pair with this one probably cannot. In this scenario, is it unique? Yeah, it may not be unique solution. One thing you need to take notes, it may not be unique solution. The pair, that means, yeah, it may not be, but the maximum number of match is unique. Yeah, the maximum number. That's why you'll find that in the assignment, in your last question, I'm not asking you to find the match, because the match may not be the unique, may not be unique. A may not be paired with B. Yeah, it can be paired with B. In the end, it may be paired with C. You also get the maximum number of match. Yeah. So same thing, you will find that in the future, if you're taking some, I think in your final year project matching, yeah, they also just match your, yeah, they're just trying to find way to find the maximum match. They're not really concerned is like who's supposed to match with which professor should select which particular student. They're just trying to use the system, just trying to use the matching algorithm to match as many students to the project, as many as possible. They're not really bothered about who will going to select this project or not. Yeah. And like I said, yes, it's possible. Yes, it can be different. Like I said, if your network have multiple solution, all give you the same number of maximum match, breadth first search and depth first search may give you different answer, but the maximum number of match should be remain unchanged. Whether you use breadth first search or depth first search, they will give you the same number. Yeah. So that is the Ford-Fulkerson algorithm matter. Yeah. Of course, this algorithm, you can see that here, in the matching problem, we assume the capacity is 1. Yeah. So you select 1 becomes 0. The capacity used up then becomes 0. The CF will become 0. The CF, after, if you select it, then the CF will become 0. Yeah. If you want to unselect the certain path, certain edge, then you will add back 1. So it's basically 0 or 1. Yeah. But it also can be applied in so-called, this is a maximum floor algorithm. That means the edge, the capacity may not be 1. It can be other number. But that is not matching problem. It is other problem already. It is a maximum floor problem. And good question. So do we need two graphs to keep track of capacity and flow. And you think about it, you see that do I need, actually you look at it, it's 0 or 1. If you look at just now the graph, yeah, the left hand side, is it important? If today you just need to know the maximum, can I get the same information from the right hand side about the maximum? What is the maximum? In this case, I think 1, 2, 3, 4, 4 match. So how do you know there are 4 match in the right hand side? I don't know whether you see it. One more time. Yeah, from the residue graph, are you able to know the maximum edge? The maximum pair, maximum match. Yeah. So because it's only 0 or 1, yeah, I would say that you may not need 2 graphs. You may not need. Well, if you build out 2 graphs, you're still able to find the answer. Not surprising. But I think I just need 1 graph. Yeah, actually the residue graph can tell me when I can stop. Yeah, finding the path. There's no more path. There's no more augmenting path in the residue graph. It also implied that we already reached the maximum flow. We already reached the maximum matching. Yeah, that means I able to, from some places, some information tell me that, yeah, what is the maximum number of match. I don't have to really record now. This one match with this one. This one match with this one. Then later this one not match with this one. And I need to match with this one. And then J5 match with W9. Right. Yeah. Okay. So another thing, I think I don't have the animation. Let me take my notes. Discuss. Where is my notes? I think in the notes I provide you. Where is the? Where is my lecture notes? Oh, last one. Not here. Where I put my stuff? Lecture notes. My lecture notes. Okay, maximum match. I need the alphabet. Help me. Yeah, there's an animation. So, yeah, it also can be, the problem also can be, okay, maximize it, close it, view in full screen. Yeah, not good. Yeah, so maybe this one will be clearer. Okay. CZ. In the lecture notes, okay, I also give you another example using the Ford-Fulkerson algorithm to find the maximum flow. When the graph is weighted graph, that's mean all this, let me play, stop, back. Okay, that's mean I give you this graph. This graph is a weighted graph, weighted directed graph. And 16, 4, 13, 12, 9, 14, 7, 20, and 4. These are the capacity. That means you allow something to flow from S to V1. The weight is 16. Yeah. Then there's a flow, there's a capacity. You can imagine is one of the application is in the railway network system. Yeah, the train can carry so many items from V1 to V3. Yeah, you can V3. There's a line from V3 to V2. That means all these V1, V2, V3, V4 are city. Yeah, different places. Yeah, maybe from London to Paris, Paris to don't know where. Yeah, from some country, some city. Yeah, then the train can carry so many items. So I need to find the maximum flow to bring my stuff from S to T. So what is the maximum flow? So using the Focusson method algorithm, I can solve this thing. So in the first path, I select this one. Maybe I use a breadth search or depth search. Yeah. Then the path will be from S to V1, V1 to V3, V3 to V2, V2 to V4, V4 to T. Yeah, this one. Then now, what is the C minimum? Just now what is the C minimum? C minimum, you look at here, 16, 12, 9, 14, 4. So the minimum is 4. So the minimum is 4. That means the maximum flow along this augmenting path is 4 only. Because the maximum you only, if you carry something from S to T along this path, you only can carry 4 items. Yeah, so I update my network graph at the left hand side. I think don't need. Yeah, already used 4 capacity. That means the flow is 4. I update. Yeah, the CF is 4. The flow is 4. So I update my right hand side. I also update my right hand side. So now I have the flow from S to V1. Original is 16. So 16 minus 4 will be 12. So after that will be 12. Then that means you can flow through here. You already use 4. That means I have to update the other direction. I can bring back that item. I can bring back 4. Because I already flow through 4. So that means I can move in the other direction. I can take back 4. Same thing. This one also update. From originally, you have full capacity. From V1 to V3 is 12. Now already use 4. So become 8. 12 minus 4. 8. But at the same time, you have an opposite direction. Can flow back 4. Then followed by this one, followed by this one, followed by this one. Yeah, this one, I just simply, if it's 0, I just simply remove it. Otherwise, the graph will be very complicated. Yeah, so I just take reverse back. Yeah, that means only can flow back 4. You already full capacity from V4 to T. Now you only can bring T back to V4. So this is one. Next, I'm trying to, from the new residue graph, after update, this is the current capacity. After adding this augmenting path, this is the current capacity available. I can use. So I will apply again. I will repeatedly apply the breadth search or depth search to find. No, I think this one probably can not really. Sorry. Finding the method, you cannot use a breadth search and depth search. You have to use some other algorithm for you to find the path. Yeah, because there's a method involved. Yeah, maybe breadth search and depth search not very good idea. I think can. I want to use it. I still can use it. I just don't care about the weight. I just find a path on it, right? Yeah. So. Yeah, okay. Then I think I still can use. breadth search and depth search to find a path. So what is the path? So now I'm trying to, this one already selected. Okay. Next, Okay, everything is updated. So you will find that there's a new, you can find that if you have a one omitting path in the network, the corresponding opposite, there's an opposite direction come out. There's an opposite path appear in the residue graph. So this is one. Then next I can find, I think I find this one, from S to V2, V1, V3 and T. Yeah, maybe using whatever, breadth search or depth search. So this time again, same thing. Not surprising, the minimum is 4. The minimum I can have 4. My capacity, my flow can be 4 in this augmenting path. I do the same thing, I update. So I update my left hand side. So you can see that this particular path just now got one from S to V1. Now to V3. There's another new augmenting path from S to V2 to V1 to V3. So you have 2. So total you already use up 8 capacity. Yeah, 8 item or whatever you name it to flow from V1 to V3. So I update. My right hand side, my residue graph is updated. Yeah, so you can see that there's a new path in the opposite direction with the flow of 4 is added. So keep doing this, carry on. I think I don't have to keep, then I find another new one from here to here to here to here. So that's means from S to V1, V1 to V2, V2 to V3, V3 to T. And along this path, 4 is a minimum. The flow is 4. So I can update, I can update my right hand side. So I'm trying to update it. So 4 is used. So you can see that the thing is this. Now you already use up, because along this path you can observe, if you take 4, this one from here you use 4, but here I don't have. Actually there's no, so you can see I'm trying to choose this one and update it in the opposite direction. So some will be minus, Okay, so carry on. So actually they only select this one and this one. Actually they cancel out. Just now we got one flow from here. Then there's when the other one is flow in the other direction. They're trying to cancel. They're trying to, actually this, if you take notes just now, this one, actually V1 to V2, no such thing in the original graph. But why there's a such, when you select this augmenting path, what does it mean? It's trying to set that earlier path, in the earlier augmenting path, there's a path, this particular edge will be cancelled. You're trying to reverse back. So you can see here, originally it's already used up. Because earlier, in the earlier previous few, I don't know whether I can go back. This one. This one already used up this particular path. So in this one is trying to set that you're trying to remove the earlier edge. There's a path, there's a flow from V2 to V1. You need to cancel it. You need to remove it to maximize your flow. So that is the interesting thing of this method. They can help you to maximize the flow. Sometimes you need to remove some edge, some path, so you can further improve the flow, the number of flow, to maximize it. So you keep carry on. You can play around with this animation. So you can see that now this one will select 8. Actually the 4 is from here. There's no more path from S to V2 to V1. So ultimate is I think this is the last one. S to V2 to V4 to V3 to to T. So maximum will be 7. Maximum will be 7. So 7 is selected. Yeah. Then after that, you update your network graph accordingly. Same thing, this one already fully utilized. So there's no more path. You can see, for example, V4 to V3. Yeah, this path in the original network graph, not surprising because I select the maximum. So this particular V4 and V3 already used it. So in the corresponding residue graph at V4 to V3, after I update, I will change the direction. That means no more. You cannot select. What does it mean? That means later in the following augmenting path you selection, you cannot select from V4 to V3. The only path you can select is V3 to V4. That means, what does it mean? If you select V3 to V4 as part of your augmenting path later, you are trying to cancel. You're trying to cancel the earlier selection. Cancel this particular one. Yeah, if you select this letter. So after that, yeah. Oh, I still got one more. Okay, I still can carry on. So I still can find a path. So same thing, I just update. I think I also maximize another one. This one also maximize already. Yeah, so there's no more. There's no more. No more from V1 to V3. Update. Yeah, so next, you will find that no more. I think this time really no more. VS to V2. V2 to V4 cannot. V2 to V1 cannot. From S to V1. S to V1 cannot. You cannot go to here. You cannot go to here. So no more. Yeah, really no more. So that is the maximum floor. So how you see? You can see from here, the floor in 19.4. So the maximum floor is 23. Yeah. You also can pick those edge. V1 to V3 fully utilized, 12 over 12. V4 to V3 fully utilized, 7 over 7. V4 to T also fully utilized, 4 over 4. So that means this is 12, 7, 4. If you cut this one, you will find that you can separate this network into two. Yeah, you can see that actually, yeah, all the floor is flowing through V1 to V3, V4 to V3, V4 to T. Total 23. 12 plus 7 plus 4, 23. So if you flip the edge, would you the breadth-first search and depth-first just keeping searching endlessly if there's no more matching? What would be? If you look at the residue terminal, at this point, your breadth-first search or depth-first search are not able to find any new path. Right. I always show you, you can see S to V2, V2 to V4, cannot, no more, you cannot reach T. S to V2, V2 to V1, V1, you also cannot move further. So you are stuck at the V1 and V4. There's no more because this one don't have pen. Do I have pen? Yeah. Okay, let me see. In Alphabet how to use pen. Maybe here. You can find that this path is already yeah. Not used to use this. Never mind. I think whether I got. So won't visit the same notes. No. You one thing is you need to take notes is I'm trying to from finding using the breadth-first search or depth-first search. My objective is trying to find the path. Find a path from S to T, from the source to the sink. Okay, so you find that after so many rounds, eventually you can't find any new path. Whether you use the breadth-first search or depth-first search, there's no more path. Now you're trying to find at the right hand side the residue. The key again, the breadth-first search and depth-first search is apply on residue graph. Apply on the residue graph. So there's no more path. You can see that right now there's no more path. From S to V1, S to V1, then no more. Cannot move. No more. There's no edge from V1 to somewhere. Yeah, you go back to S. That's when you actually S is no breadth-first search or depth-first search. S is visited already. At that point, first you put S After S is visited, you're trying to visit V1. V1, then there's no more unvisited nodes available. Stop. Okay, cannot. So you try another path. S to V2, V2 to V1 already visited. I will try V4. V4 cannot, no more. Then after that, there's no more nodes. No more nodes. This means I'm not able to find a path from S to T. I terminate. Yeah, so you apply breadth-first search or depth-first search, you will get the same result. You will stop here. Agree? And then you're trying to find the cut. Actually, you can find that there's a cut. That means here, this particular edge is fully utilized. This particular edge, V4 to V3, is fully utilized. This particular edge, V4 to T, is fully utilized. So these three edges form a cut. Is known as min cut. Min cut means that actually, did I put? Yeah, min cut. Yeah, the total weight of this edge equal to the maximum flow. Yeah, it's known as min cut. Because you find other cut, yeah, definitely more than 23. Right? Because they are not fully utilized. Definitely more than 23. 12 plus 9 plus 14. I mean the capacity. I sum the capacity. 12 plus 9 plus 14. Larger, right? Yeah, you can find any cut. Yeah, only this particular cut, the sum of their capacity, the sum of their weight or capacity, yeah, is minimum. So-called min cut. Okay, that is another application of maximum flow for you to find. So before I end today's lecture, the last part, yeah, so that is the maximum flow. Yeah, I'm introduce you the fault focuser method, which is solving the maximum flow problem. Yeah, then this particular problem is just nice. Maximum match is a special case, which the capacity only can be 1 or 0. Yeah, no capacity or 1 capacity. So you can use the maximum flow algorithm to solve this matching problem. And basically, in short, this one is trying two elements. One is finding the augmenting path. And first element is the residue network to show you the remaining available capacity in the network. And then second thing, the key item is augmenting path, finding augmenting path. It can be using the breadth-first search, it can be used the depth-first search. Yeah. So, yep. So matching problem is 0 or 1 or unweighted graph, or you can think that way. So the implementation for compared to general maximum flow problem, matching problem, yeah, the implementation is easier. Then yeah, one of the application just now I mentioned, yeah, is in this thing, why it come out in 1956. Yeah, that is due to the Cold War. Yeah, at that times, yeah, so they want to find the path. Yeah, what is the bottleneck? Yeah, it's somewhere here. It's along here. Yeah, from this part, this C all the way cut. Just put some bomb here and here. Okay, then they will broken the whole network into 2 pieces, and they can find out what is the capacity. Yeah, they can carry how many army resource through this railway network. Yeah, so in the end they find there's a cut on the maximum flow is 163,000 tons. Yeah, that is the bottleneck from Russia to Eastern Europe. Yeah, in 1950 something. Yeah. Well, another application is in, I think in the earlier I also mentioned about this computer vision. Yeah, they can use this thing. Okay, this thing need to show you in. Yeah, in fact, in your PowerPoint, there's this particular stuff. Yeah, remove background. Yeah, then you can add some edge. I can add some, I want to keep this particular bars. I'm trying to put some, all these are the so-called the source. And then I'm trying to keep, I want to remove all, then the background I will indicate as the sink. So they start calculating what is the maximum flow in this. The capacity, all this they were trying to reformulate to find the discontinuity in the image. Yeah, so I think I keep adding. Eventually they were able to remove all the, yeah. Today so unlucky. Just a wrong graph. Yeah, sometimes I think they can perform very well. Yeah, okay, almost. Maybe keep a few more. Yeah, maybe positive side I put more. They're trying to find the edge. Basically, they're trying to find the edge to find the best cut along. Yeah, but maybe a bit hard because I want to cut this one. The edge is not clear, so maybe they're very difficult to cut. But I think I add a few more, they should be able. Yeah, especially closer to the bus. Yes, closer to the bus, I can get a better cut. Yes. Yeah, that is actually behind. They are actually implement a maximum flow. Okay. Yes. Okay. So that is what I'm cover for this module. I think Wednesday I will give an overview or clarify your doubt for the second part. Basically, we look at the remaining of capacity when yes. The idea behind of this problem, this algorithm, the key thing is they're trying to have a residue network. This residue network provide you the information is like what are the available path for you to have finding more flow, to get more flow flowing through. Yeah, that's why they need to introduce a residue graph to keep track the available path for you to add in. So they can iteratively, every iteration, you find more path, implied that you find more, your flow is increasing, or the number of match increasing. Yeah, until you can't find any new flow in the residue graph. That means you already maximize it. You won't be able to find any new. I think one more thing, last thing in the lecture notes. I think I didn't mention too much because that is not the thing I want to I just let you know that actually, yeah, breakfast search version, yeah, is better lah. Actually, yeah, someone in 1972 have been proposed. There's this one called Matter because there are a lot of version, a lot of algorithm. Yeah, there's another two person, Jack Ammon and Richard Clark. Yeah, they propose another algorithm using the breadth-first search. Actually, I think more or less is similar to the Ford Fulkerson original algorithm. He just improved it and then to find the shorter path. Then there's some proof. I don't want to discuss further. That's why I just let you know that the complexity is this. Yeah, and then over the year, even until 1998, yeah, people still keep trying to propose. Because the key here, you find that actually how you select the path, yeah, can increase to let it converge faster, to maximize the flow. yeah, is the key. One in this particular matter, but how to find the path can quickly let you find the maximum flow. Yeah, so yeah, everyone were trying to over the past near 50 years, more than 50 years. Yeah, they keep propose different solution. Yeah, that's people what they are doing the research in this particular problem. And if you quite well, I think all this is again is related to optimization. In mathematics is in the optimization problem. Yeah, you're trying to optimize, you find the optimum solution. Yeah. So that is the application, yeah, of about this algorithm. Can be in railway, can be in transportation, can be in image processing. In fact, a lot. Matching is in our daily life, a lot of problem are matching problem. Yeah, a lot of, like you select project, yeah, you want to find the matching. Yeah, or you select certain courses. Yeah, sometimes we need to do the match. Okay, any question? If not, that is today lecture, and Wednesday will be the last lecture, and will be just revision and clarify your doubt. Okay, if no further question, that's all today. Okay, I think no more. Goodbye.